Okay, in that last section, we talked about several hormones that are involved in regulating water reabsorption, aldosterone and vasopressin, and how both of those hormones cause us to reabsorb more water from the urinary tubule, which will take that water away from the urine, so we make less urine, and put it back in the body, so we add to blood volume, which changes blood pressure. So now we want to talk about how those hormones are controlled, especially aldosterone. We'll get into vasopressin a little more later. Now, before we do that, I also wanted to point out, we're going to tie this into the idea of renin. So the overall topic we're talking about here is kidney involvement in blood pressure. So how are the kidneys involved in regulating blood pressure? Now, I asked you to make a list of things that caused renin secretion. And if I remember correctly, we had several things. So we had low flow past the macula densa. That caused secretion of prostaglandins, which led to secretion of renin. A second one was low stretch in the afferent arterioles. That also led to the production of renin at the juxtaglomerular cells. A third one was activation of beta-1 receptors on the juxtaglomerular cells. That would come from sympathetic activity. Epinephrine in the blood, or norepinephrine from postganglionic sympathetic cells. So these three things all produce renin secretion. And please note that these first two are associated with low blood pressure. So for these two in particular, low blood pressure can produce low GFR, which produces low flow past the macula densa, and low blood pressure will not stretch out the afferent arterioles as much. So in two of these three cases, renin secretion can happen as a result of low blood pressure, which, based on what you know about how negative feedback works in the body, might make you think that renin is going to have a role in raising blood pressure, and it does. In fact, we talked about, when we did cardiovascular system, ways that the body regulates blood pressure. We mentioned the short-term method of the baroreceptor reflex, where we have stretch receptors in the carotid arteries and the aortic arch that respond to stretching or less stretch in those arterioles by changing sympathetic, parasympathetic nervous system activity to fix blood pressure so that we make sure we get enough blood supply to the heart and brain. That is the short-term method for blood pressure regulation. That happens at the scale of seconds to minutes. We're going to talk now about the longer-term method, which happens over this course of hours to days to weeks. That is something called the renin, angiotensin, aldosterone system. So this is going to be the renin, angiotensin, aldosterone system. It's going to be a way that the kidneys, by secreting or not secreting renin, can influence the production of a couple of hormones, including aldosterone, which are then going to affect blood pressure. So let's go over how that works. So our overall big picture view of this starts with the idea that we have low blood pressure, which results in the production of renin, which is a protein produced by the juxtaglomerular cells and secreted into the blood. Now, what is renin going to do? Well, to answer that, we have to bring in one other thing. Our liver is constantly secreting a protein called Angiotensinogen. So, Angiotensinogen is a prohormone. it's a protein hormone, but it has a piece on it that is preventing it from being active. So you could almost think of it as if this is our hormone, it's got some piece stuck on it that's inactivating it, keeping it from being an active hormone, not letting it bind to receptors. That's angiotensinogen. Do notice this ending, ogen. You'll see this a lot. You've already seen it some, like fibrinogen. When you see things in the body whose name ends in ogen, that implies that this is the inactive version, or at least less active version, of something else. This is going to be made into something else, like fibrinogen became fibrin when thrombin cut off the part of it. Angiotensinogen, on its own, doesn't do anything. It just circulates in the blood. It's an inactive hormone. But we're going to be able to activate it and turn it into something else. What's going to activate it? Well, that's the job of renin. So normally my liver has put angiotensinogen into my blood and it's circulating and doing nothing. But when renin shows up, renin acts as an enzyme. SNP cuts off the part that's making this inactive and turns this into angiotensin I. Angiotensin I also doesn't really seem to do anything. There's a little bit of debate about whether it has any activity at all, but even if it has a little, it's not much at all. So angiotensin I really doesn't do much, or possibly nothing. But angiotensin I can be made into something that does do stuff. Angiotensin I can be made into, here's the creative name, angiotensin II. And angiotensin II is powerful stuff. Angiotensin II is a powerful vasoconstrictor. Angiotensin II causes blood vessels to tighten up all through the body. Major arteries, arterioles, all of that. If you imagine all of the arterioles tightening up, that increases peripheral resistance a lot, which will raise arterial blood pressure significantly. It also stimulates secretion of aldosterone. And as you know, aldosterone is a major hormone involved in regulating water retention at the kidneys. More aldosterone means we pull more water back out of the urine, which puts that back into the blood, which raises blood pressure. It also stimulates vasopressin secretion. That's probably not as important of an effect. It probably doesn't have as much effect on vasopressin secretion, but it has a big effect on aldosterone secretion. It's the major thing that causes secretion of aldosterone at the adrenal cortex. Now, one question that comes up here is, what converts angiotensin I into angiotensin II? We know that renin converts angiotensinogen to angiotensin I. So what does this step? There's another enzyme. Now I want you to imagine for a moment that you are a scientist that has discovered the enzyme that does this. What are you going to name it? You might come up with something, renin is kind of a cool name, but you aren't feeling that creative. So what you decide to name it is angiotensin converting enzyme. Very great. So, angiotensin converting enzyme turns angiotensin I into angiotensin II. And angiotensin II, through several mechanisms, constricting blood vessels, stimulating aldosterone secretion, and to a lesser degree vasopressin secretion, increases blood pressure. So, low blood pressure caused the production of renin, which converted this existing thing that's already there, the liver's already put it into the blood, into a hormone, which is converted into another hormone, which goes back and raises blood pressure. A nice negative feedback loop. Now, one last thing here. This is not a very creative name, but they snuck something fun in there. Take a look at the initials. ACE. And if you have ever heard of a drug called an ACE inhibitor, that is the ACE which is being inhibited. ACE inhibitors are given for hypertension, for high blood pressure. So if you take an ACE inhibitor, you limit the activity of angiotensin converting enzyme, which limits how much happens here. So we get stuck at angiotensin I, which doesn't really do anything. That means you don't produce as much angiotensin II, which means you don't have these effects that increase blood pressure, so it tends to drop blood pressure. Now, another side note on that one. As it turns out, the coronavirus, which is causing so much trouble right now, the SARS-CoV-2, I think that's what it's called. Anyway, the one that causes COVID-19, seems to invade the body using an ACE2 enzyme. The ACE is expressed mostly in the pulmonary capillaries. Why there? I'm not sure. But this enzyme is mostly put out in the blood vessels in the lungs. As it turns out, the current coronavirus, which is causing us problems, seems to be able to latch on to one version of this, ACE2, and use that to enter the body. Just a minor point that's kind of an interesting current relevance of this. So, just to summarize this, in terms of kind of longer term, hours, days, weeks, regulation of blood pressure, our kidneys detect low blood pressure, that's the less stretch on the afferent arterioles or the low flow at the macula densa, and secrete renin. Angiotensinogen circulating in our blood, when it finds renin, gets converted to angiotensin I, which is converted by ACE to angiotensin II, which raises blood pressure by stimulating secretion of aldosterone, vasopressin, and constricting our blood vessels. So that goes back and fixes that problem. Now you remember, renin also came from sympathetic activity acting on those juxtaglomerular cells. Sympathetic activity directly constricts blood vessels a lot. Remember those postganglionic sympathetic neurons synapsing onto smooth muscle around blood vessels and mostly acting on alpha-1 receptors, although there are exceptions. This is another way that sympathetic activity raises blood pressure. It increases renin secretion from the kidneys, which activates this renin-angiotensin-aldosterone pathway. This is an important one. You find this is important for clinical medicine, so you will want to know this reasonably well. Okay, that is the end of lecture US-2. In the third lecture of the urinary system, we're going to have a lot to cover. We're going to cover how the urinary system handles fluid balance, how it makes sure that when you take in water, you get rid of as much water as you need, and how it's involved in regulating pH. See you then.